And welcome. Today, we're going to do a deep dive and absolutely unlock one of the trickiest questions from the recent chemistry exams. If you've ever been stumped trying to compare organic compounds, trust me, you are in exactly the right place. So, we are putting question 3 from the November 2024 paper under the microscope. This one is specifically designed to test your real understanding of intermolecular forces, and honestly, it's a perfect place to really show the examiner what you know.
And get this, it's worth a massive 11 marks. That's a huge chunk of your paper, right? But don't worry, by the end of this, you are going to have a rock-solid strategy to nail down every single one of those marks. Let's get into it. Okay, so here's the setup. We're given a table with 5 different organic compounds. We've got some data, things like molar mass and vapor pressure, and our mission is to figure out the story that data is telling us. So let's take a closer look at our lineup. First up, we have compounds A, B, and C. That's pentane, 2-methylbutane, and 2,2-dimethylpropane. Now, what's the first thing you notice? Look at their molar mass, all 72. That is a massive clue right there. It tells us they're isomers. Then you've got compound D, propanoic acid, and compound E, butanal. And you'll see the vapor pressures for A, B, and C are missing. That, my friends, is our first puzzle to solve. Now, before we jump into comparing anything, we have to be 100% clear on the key term here, vapor pressure. Seriously, getting this definition perfect is step 1 to grabbing some of the easiest marks on the paper.
Okay, look closely. This isn't just a definition. This is the exact definition, word for word from the official marking guidelines. My advice, pause right here, write this down, and burn it into your brain. It's basically 2 free marks just waiting for you, because it's precisely what they're looking for.
But to really understand it, let's think about it this way. Vapor pressure is just the escape tendency of a liquid. It's how badly those liquid molecules want to break free and turn into a gas. So if a liquid has a really strong desire to escape, a high push, we say it has a high vapor pressure. Simple as that.
All right, let's get back to the first part of our question. We're comparing A, B, and C. Remember what we said? They're structural isomers. Same atoms, same molar mass, but they're built differently. They have different shapes. This is a super common comparison they love to ask about.
So the paper gives us 3 vapor pressures and asks us to match the highest one, 146 kilopascals, to one of the isomers. The big question is, how do we figure this out? What's the logical process that not only gets us the right answer, but also gets us all the explanation marks? I'm going to give you a foolproof 3-step method for any question like this. It never fails. First, we look at the molecular shape. Second, we figure out how that shape affects the intermolecular forces. And third, we connect those forces to the energy needed to escape, which directly gives us the vapor pressure. Shape, forces, energy. Let's try it.
Okay, step 1, shape. Let's line up our isomers. Pentane is just a straight line, 2-methylbutane has one little branch, but compound C, 2,2-dimethylpropane, it's got 2 branches hanging off that middle carbon. It's easily the most branched of the 3, which means it gets all scrunched up into a compact, almost spherical shape, and that gives it the smallest surface area.
Step 2, forces. So what does that compact shape actually do to the forces between the molecules? Well, because compound C is basically a little ball, it has way less surface area to interact with its neighbors. Think about it. Would it be easier to stick 2 long rulers together or 2 marbles? The rulers, right? They have more surface area to connect. It's the same idea here. A smaller surface area means weaker, sticky attractions between the molecules, specifically weaker van der Waals forces.
And here's the final piece of the puzzle. Energy. Since those sticky forces holding the molecules together are so weak, it takes way less energy for a molecule to just break free and fly off. That means more molecules can easily escape into the gas phase, creating a bigger push. And that, my friends, gives us the highest vapor pressure. And there you have it. The logic holds up perfectly. The most branched, most compact molecule has the weakest forces, and so it has the highest vapor pressure. The 146 kilopascals has to belong to compound C. See how that 3-step process just walks you right to the answer every single time? Awesome. Now, let's move on to the second big comparison in this question. We're changing gears a bit. We're no longer looking at isomers with the same functional group. We're now comparing compounds with totally different functional groups. It's compound D, propanoic acid, versus compound E, butanal.
Okay, let's get this straight. Propanoic acid is a carboxylic acid. Butanol is an aldehyde, and the absolute game changer here is the main type of intermolecular force in each one. Propanoic acid can form super strong hydrogen bonds. Butanol, on the other hand, only has the weaker dipole-dipole forces. This one difference in the type of force explains everything else.
And this is a rule you have to know inside and out. Hydrogen bonds are the champions, the heavyweights of intermolecular forces. They lock molecules together so much more tightly. Because the forces in propanoic acid are so incredibly strong, it's really, really hard for its molecules to escape. And what does that mean? A super low vapor pressure, only 0.32 kilopascals, and as a result, a much higher boiling point.
So getting the right answer is great, but writing it down in the language the examiners want to see, well, that's a whole other skill. Let's peek behind the curtain and see exactly what phrases you need to use to get every single mark. This comes straight from the marking guide.
For that first comparison about the isomers, you have to use the key words. The examiner literally has a checklist, and they are looking to tick boxes for words like more branched, more compact, or smallest surface area. You have to use their language.
Next, you have to explicitly connect the shape to the forces. Don't just imply it, state it clearly. Say that the compact shape leads to weaker intermolecular forces. And if you really want to show off, specify that you're talking about van der Waals forces. And for that second comparison, it's the same deal. You get marks just for correctly identifying hydrogen bonding in the propanoic acid and dipole-dipole forces in the butanol. Then you just add that the hydrogen bonds are stronger, and that explains everything. Boom, all the marks are yours.
Fantastic work, everyone. We have just completely taken apart an 11-mark question. And in doing that, we've actually built a powerful toolkit of ideas that you can use on tons of other questions. Let's quickly recap the main rules we've established.
This right here, this is your new chemistry toolkit. Memorize these chains of logic. More branches means a more compact shape. A compact shape means weaker forces, which means a higher vapor pressure. And never ever forget the force hierarchy. Hydrogen bonds beat dipole-dipole forces every time. And stronger forces always mean lower vapor pressure and a higher boiling point. This is your key to so many problems.
And just like that, we've conquered question 3. If this breakdown was helpful and you want more tips and tricks to absolutely smash your exams, please make sure you hit that follow button on TikTok and subscribe over on YouTube. Keep up the awesome work, drop any questions in the comments, and I will see you in the next one.